So now the idea is to look on the Fourier transform and the inverse Fourier transform of a simple function. Um, so let's look at it. So we take a very simple function cosinus of 2 pi t, and we want, which is, this has an amplitude of 1 and the frequency is 1 hertz, and we want to see how we take the Fourier transform of the function, gets the Fourier transform, learn that the Fourier transform is constructed of frequencies of omega, which is 2 pi f equals 2 pi, namely the frequency is 1 and minus 1, and taking this, the Fourier transform of a function, and plugging in the inverse Fourier transform function, I use the coefficient 1 divided by 2 pi. There are different coefficients, there are very different conventions for the coefficient on the Fourier and inverse Fourier transform. It's just normalization and preserving the norm of the values. Anyway, we took the inverse with 1 divided by 2 pi. This is the inverse Fourier transform. We will plug the inverse Fourier transform on the function, and eventually we should reconstruct the function. So in the Fourier transform process, we are taking the function in the time domain and we are converting it to understand it in the frequency domain. We took the cosinus function of 2 pi t, and we converted and got the Fourier transform, which is not zero, into frequency, the frequency of the cosinus 2 pi, which is a frequency of 1 and minus 1 hertz. Then we took the frequency domain, the Fourier transform, plugged it in the function for the inverse Fourier transform, and reconstructed the original time domain function. So we took it from the frequency domain, which is the function after the Fourier transform, and using the inverse Fourier transform, reconstructed it in the time domain. So let's see how it goes. So we take the cosinus 2 pi t, this is the simple function we chose, and we plug it in the formula for the Fourier transform, which is this. Again, the convention for the coefficient is, there are some conventions. We took this with coefficients of 1, as you can see. So this is the formula for the Fourier transform we are using. So plug in the function we use and we get this one. Now use the other formula for cosinus. Remember that cosinus 2 pi t can be uh, written as this using exponentials, and plug this in and we get this. Now open up the open up this and you get this formula, this function. Now you can, using exponential multiplication rules, you can get to this. This is 2 pi minus omega I and t here. Okay, so this again, use the rules of exponential and get this. So this is Fourier transform. Now remember, the identity that you can look at this as if it was a Dirac delta function with this value inside. So all this integral is this Dirac delta function. This is an identity. And this integral goes to this Dirac delta function. This is again an identity with 2 pi plus omega inside the delta function. Okay, this is the Fourier transform. When the Fourier transform is non-zero, it is always zero. The Dirac delta function is always zero, except, remember, and this is important, delta function, Dirac delta function. Let's see if I can show you it's important. So this one, this is very good. Remember this. Dirac delta function is zero anywhere except when what inside of it is zero. So if it's zero, the value is infinity. But for every other value inside the Dirac delta function, the function is zero. So we use this property. And when the Fourier transform will not be zero, in two places. One is when here it is zero, and one when this one is zero. Anywhere else, plug in any other value. When this one and this one is not zero, you get 0 and nothing. So when you won't get zero for the function is when omega minus 2 pi is 0, namely omega is 2 pi, and omega also equals 2 pi f, so the frequency is 1, and here it will be 0 only when omega will be minus 2 pi f, minus 2 pi, and omega equals 2 pi f. It's the angular frequency, and the relation to frequency is 2 pi f, omega equals 2 pi f. So if omega is equals minus 2 pi, and omega equals 2 pi f, so the f is minus 1. So we got two frequencies, mine and 1 and minus 1 hertz. So we change our function from the time domain to the frequency domain. Now, what we are going to do is taking the Fourier transform, the function in the frequency domain, and using the inverse Fourier transform, we will convert it back to the time domain. So we will get back our function. The coefficient will be divided by 2, but we will ignore this, uh, divided by 2 pi, and we will ignore this for the reason that I'm not going to work on the coefficients, because different conventions for the Fourier transform have different coefficients. So let's ignore the coefficient a little bit. So this is the convention we use. This is the formula for the inverse Fourier transform to get from the time domain to again to the frequency domain. From the time domain after the Fourier transform to the frequency domain to our original function in the time domain. Okay. So our function, original function, the time domain, this is the inverse Fourier transform. Then we take the Fourier transform and we return it to the time domain. So let's substitute the Fourier transform we got here, and we get this one. So we got this one, so we can take this exponential and get it inside. Now look at this. This is an identity. We can use this. This is the shift of the delta function. What do I mean? Look at this. Look at, oh no, not this property. Direct delta function. Okay, this one, what I need. Look at this. Look at this identity. Integral for infinity to minus infinity of the Dirac delta function x minus a at the a point, integral by x, for any other function f of x equals f at this point at a. This is an identity, and we will use this, so remember it. So now, here it is, it's the same. Now, this is our function, any arbitrary function which depends on omega, and this is what we need. F of x depends on the function we are integrating, the variable we are integrating by. So, this is exponential as a function of omega, and we integrate as a function of omega. Here is the Dirac delta function. The 2 pi is like the a in the formula. The 2 pi is for the a in the formula. Therefore, we'll get the function here with 2 pi in our case. So we'll get the function here with 2 pi in our case. Okay? Again, the coefficient, let's a little bit ignore it, but this is the coefficient. It came from here, and from here the half from here. Never mind the coefficient now. Okay, so we'll use this, what is called shifting property of the delta function, and we will get this. Now, what is it? What is it? This is exactly what is cosinus 2 pi equals to, right? This is exactly what cosinus 2 pi equals to, except for the denominator, which instead of being 2 is now 2 pi. Yes, you can take this equation and reconstruct it in this way, just with the denominator of 4 pi instead of 2 pi. This is because this coefficient right here, the convention we use, if you will use another convention without the coefficient, you will get exactly what you need. So here I can translate it to exactly what I need, cosinus 2 pi t. Again, there is a denominator here of 2 pi, we ignore it. Okay? So we use this shifting property of the Dirac delta function, and therefore we calculated it and got this, and this is the cosinus. So you saw how I took a function in the time domain, put it inside the Fourier transform, make it in the frequency domain. I could learn about the frequency of the function. Then I use the inverse Fourier transform to go back from the frequency domain to the time domain, and I reconstructed the function. Sometimes we can use converting the function, the signal, to the frequency domain there in the frequency domain, doing some processing, removing frequencies, adding to frequencies, removing frequency that is noise, things like this. And then after we are working on the frequency domain, which may be more convenient because we know which frequencies we want to remove and we can do it in the frequency domain very simply. Then after we are clear in the frequency domain, removing things that we don't need, we reconstruct it using the inverse Fourier transform and goes back to the time domain, where here we will have the signal without after the processing in the frequency domain. So this is using Fourier transform and inverse Fourier transform on a signal here on a function which is a periodic function, cosinus function, Fourier transform and inverse Fourier transform. And we use the convention with this. There are different conventions. Let's show you different conventions. There are different conventions here. This is a convention of Fourier transform and inverse Fourier transform. There are all others. There are like this. There are others like this and like this. And maybe maybe he was wrong in here. No, not here. The conventions are this one and that one. You can see the coefficients are different, but except for this, this is the same formulas. Okay, so there are different conventions for Fourier transform. This convention preserve the norm. This convention doesn't preserve the norm of the signal. This is the reason we didn't get exactly cosinus 2 pi t like the first place. Okay, so this was about the Fourier transform and inverse Fourier transform of a periodic function. I took a simple example to show how it works. Thank you very much. If there are any correction or mistakes, please correct me, and that's it.